We are in Tarnos, a small town on the French Atlantic coast. Here on this green field, construction of the world's first functional fusion reactor will begin in the next few days. We are on schedule. The truck delivers all the parts of the reactor. A 25 centimeter stainless steel ball, which will now become the reactor housing. A few threaded rods and screws, an old audio amplifier, a disused car battery, an old pulse generator, a small flask with heavy water D20, as well as piezoelectric sonar components, a water pump, a pressure sensor, a glass tube with tritium, an infusion bag, syringes, etc., with expenses to date of around $100. Here, some components are manufactured with the utmost precision using state-of-the-art technology. Six piezo elements are attached one after the other to the spherical surface with adhesive. The outer structure in the form of threaded rods and retaining elements is screwed on. There are connections for the external hydraulic circuit and for a pressure sensor at 3 points on the reactor housing. The sonar elements are attached to the North Pole, South Pole, and at equal intervals along the equator and screwed to an outer structure. This is followed by the installation of the hydraulic circuit, which connects the upper outlet connection to the circulation pump and then to the inlet connection. One of the thicker hoses contains the undamaged glass tube with tritium. A pressure sensor for monitoring the sound waves generated is connected to the third connection. All sonar elements are connected in parallel. The assembly of the reactor is now complete. The reactor is filled with water with great care, as this water must not contain any dissolved gases. To remove the gases, the water is boiled and then fed into the reactor and infusion bag as hot as possible. While the water cools, the deuterium is obtained by electrolysis of heavy water D20. This is easy to do. A tube closed at one end with 2 electrodes is filled with heavy water, to which a drop of sulfuric acid from the battery has been added. The tube is bent into a U shape. Direct current is applied to the electrodes. After a short time, deuterium forms at the negative electrode and oxygen escapes at the positive electrode. The tritium is already in the reactor but is not yet in contact with water. To release it, the glass tube is broken from the outside. The tube was 90 millimeters long and had an inner diameter of about 3 millimeters. The volume of tritium is therefore approximately 600 cubic millimeters. An equal amount of deuterium is extracted from the electrolysis device using an injection needle and injected into the hydraulic circuit, and the puncture site is sealed. The fusion fuel is now in the water and still needs to dissolve. This is best achieved at low temperatures. To do this, the reactor remains in the refrigerator for a while with the circulation pump running. The infusion bag compensates for the reduction in water volume caused by cooling. The control electronics for operating the reactor consists of a special pulse generator that controls the sonar elements via the audio amplifier. The pulse generator can generate a freely configurable double pulse with variable frequency. This double pulse is essential for the functioning of the fusion reactor. It generates voltage changes at the piezo elements of the sonar system.
Écoute bien ce qu'on me raconte.
The front pulse generates a contraction, and the subsequent rear pulse generates an extraction of the sonar. These changes in length are very small, at around 2 to 3 micrometers. Contact with a thin reactor wall generates sound waves inside the water-filled reactor. The sonar elements are controlled in such a way that the sound waves overlap exactly with the reflected waves, i.e. with the natural frequency of the hydraulic system, which in our case means approximately 6,000 sound pulses per second at a sound velocity of 1,400 meters per second and a reactor diameter of 250 millimeters. Normally, spatial sound waves attenuate with distance from the sound source. However, different laws apply within a spherical space. The amplitudes of the sound waves change depending on distance from the center of the sphere in a ratio of 1 divided by distance from the center of the sphere. The sound wave generated at the reactor wall begins with a slight drop in pressure, after which its pressure increases sharply. When this sound wave reaches the vicinity of the reactor center, its wave head has dropped in pressure to such an extent that it falls below the vapor pressure of the cold water, and microscopic cavitation bubbles are formed. The size of the front pulse therefore determines in which area of the reactor cavitation bubbles form. The cavitation bubbles contain steam and the gas previously contained in the evaporated water, i.e. deuterium and tritium. The pressure drop of the sound wave is followed by a sharp rise in pressure. The vapor pressure is exceeded again and the vapor condenses into water in the form of mist. The cavitation bubble implodes, causing the deuterium-tritium mixture remaining in the bubble to undergo adiabatic compression. The implosion ends when the compression pressure in the bubble is equal to the external pressure at the bubble wall. The pressure conditions near the bubble are complex. The local liquid pressure initially acts on the cavitation bubble. During the implosion, an independent inward moving spherical wave is then generated, which causes a further increase in pressure. Thermodynamic calculations show that at the end of bubble collapse, gas temperatures of several million degrees Celsius and point pressures of over 10,000 bar are generated, values that are more than sufficient for igniting fusion. The less dissolved gas there is in the bubbles, the higher these values become. When nuclear fusion occurs in the cavitation bubbles, a great deal of energy is released in the form of neutron radiation and heat. In our reactor, the local heating generates large pressure waves in the reactor fluid, which are converted into electrical energy when they hit the sonar element. Anyone interested in the thermodynamic and hydraulic processes involved here can find further information and calculations online under the keyword hydraulically induced nuclear fusion. Friends and neighbors have come to witness the first test run of the fusion reactor.
Chers amis, chers voisins, dans quelques instants, le premier réacteur de fusion nucléaire opérationnel au monde sera en service. Porterons un toast.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Tu as filmé, Daniel?
Mais non, j'ai eu peur.
Maintenant, je sais pas la vidéo. C'est nous, hein. Non, mais était peut-être là. Ah, ben voilà. Faut même danser.
Maintenant, c'est...
Fallait que ça sorte un peu. Fallait que ça sorte. Le coup de village.
Fusion nucléaire a commencé.
The nuclear fusion age has just begun.